In this lesson, we're going to talk about transformations of functions. Transformations is just a way that we can use to graph particular functions. And in order to graph function by transformations, we need to be able to graph the simplest form of each sort of function that we can think of. So for example, if we want to graph parabola, we need to be able to graph the simplest parabola we can think of, which is y equals x squared, and that's a parent graph. So in order to graph something like y equals x squared, we need to put in some nice numbers for x. So I'm going to pick -2, -1, 0, 1, and 2. What I'm going to do is I'm going to put these into our function and then see what pops out for y. So we've got -2 all squared is going to be 4, -1 all squared is going to be 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And so let's quickly sketch those points on this graph here. So here are the points. We know that this is going to make a parabola. So we're going to connect these two here. Ta-da. Okay. So we need to be able to come up with these points very, very quickly because we're going to always start with them before we start graphing more complicated parabolas. So you'll see what I mean by that on the next page. But now that we know the basic points of this parent function, let's do the basic points of another parent function, y equals sine x. So I gave you here the x values that are going to work well, 0, 90, 180, 270, and 360. So if you put in 0 into here, sine of 0 is going to be 0. Sine of 90 is going to be 1. Sine of 180 is 0. Sine of 270 is -1. And sine of 360 is 0. So if we are going to plot these here, we need to come up with a scale. So we need to get all the way up to 360. So I'm going to count 3 dark lines and say that that's 90. So we've got 90, another 3 dark lines, and we have 180, and then 270, and 360. For our y, we can see that the highest y value is 1 and the lowest is -1. So I'm just going to make this one 1, this one -1. And I'm just going to close out, here's our y-axis, and let's just plot these points. So I'm going to plot 0, 0, and then we have 90 and 1, and then 180 and 0, and then 270, -1, 360, and 0. And let's just connect it. We know what the sine graph looks like. It's a smooth curve connecting these points. It looks something like this. Okay, so both of these graphs together make up 2 different parent functions, so like original functions that we're going to start with. So we need to be able to sketch each of these very quickly and come up with the points really quickly. Let's start transforming now. So we are going to start with the parent graphs that we know, so y equals x squared and y equals sine x, and we're going to start adding and subtracting numbers to it and see what ends up happening to the graph of them. So please graph the following using Desmos. So open up Desmos and plot in y equals x squared plus 3, y equals x squared minus 4, and then come back to the video. So here's what you should have gotten. This middle guy, that was our original parabola, y equals x squared. This one on the top here, this was the second parabola, y equals x squared plus 3. And this one at the bottom was y equals x squared minus 4. So what has happened here to each of these parabolas as we add and subtract numbers? So when I added a plus 3, what ended up happening? Here's our original. It ended up moving the parabola up 3 units. So here it started at 0, now it's at 3. This point was at 1, now it's at 4. So adding 3 on the outside of the equation ended up moving all the points up 3. And how about the green one? Take a look at the original equation, y equals x squared. What happened here to get the green one? Well, all the points got moved down 4 units. 1, 2, 3, 4. Here, this point was at 1, now it's at -3. So this moved the parabola down 4 units. So this looks logical. You add 3 on the outside of a function, it moves it up 3. And if you subtract 4 on the outside of the function, it moves it down 4. What if we add 3 and subtract 4 to another function like sine x? So here's the other parent function. We can plot into Desmos, but it's going to do the same thing. It's still going to move it up 3. And if we subtract 4 from the function, it's going to move it down 4. So what if we try another transformation? What if we add and subtract numbers in a different place? So take a look at these comparisons. So if we start with y equals x squared, and then what if I put the plus 3 not on the outside like it was here, but on the inside beside the x? So the inside where it's inside where the squared is. What would happen? What about the 4? What if I didn't what if we didn't subtract 4 on the outside? Instead, we subtracted 4 on the inside of the function, inside the squared. So plot these 3 into Desmos and see what happens, and then come back to the video. So here's what you should see in Desmos. This middle guy here, that was our original, so that was y equals x squared. This blue one was what it looked like when we did x plus 3 all squared. And this green one, this green one was the last one, y equals x minus 4 all squared. So what happened? When we add and subtract numbers inside the function, it didn't move it up and down anymore. It moved it left and right. And so what happened here? Here's our original. It looks like we added a 3 to x, and where do we go? We went to the left. We went left 3 units. So it went from 0 to negative 3, 1 to negative 2. So we went here left 3 units. And what about this guy here? What happened here? Here's our original. It moved everything to the right 4 units, every point from 0 to 4, 1 to 5. So we went right 4 units. So anytime we're adding or subtracting numbers inside of the function, it moves it left and right. And when it's on the outside of the function like this, it moves it up and down. What about for sine? What if we were to add and subtract 3 inside the sine function? Well, here we're inside the function. Let me show you in comparison what it looks like when it's outside the function. See where these 3's and 4's are? Here the 3 is outside the sine x. Here it's inside the sine x. So this would take sine x, and just like here, it would move it left 3. Left 3. And this guy here, see how this minus 4 is inside the function? It would do the same thing as this parabola. It's going to move the whole function right 4. So let's summarize this together. So we can call, just so that we're on the same page with what we're going to call, what number we're talking about. We can call any numbers outside the function as D, and we can call any numbers that are added subtracted inside the function C. Just, you don't need to memorize this, just so that we have an idea of what numbers we're talking about. So when we're adding or subtracting a number outside the function, this is going to move it up and down. So there's one little error here. We're going to change this to D and D, not C and C. So when D is greater than 0, what ended up happening? So when this number was bigger than 0, we'll take a look at this one here. When this number was positive, it moved it up. So up that many units. So if it was positive 7, it would move it up 7 units. And when the number's negative, so like here, it moved it down. It doesn't matter what the original function is, no matter what it is, it's going to move it up or down. How about C, this value on the inside here? When C was greater than 0, it looks like this, right? Actually, C is defined as whatever is beside the negative. So I want to just change something so it makes a little bit more sense. Change this to when C looks like, C is greater than 0, and when it looks like C is less than 0. So let's zoom out so we can see this. Okay, so here's an example. This is when C looks like it's greater than 0. It looks like it is. It looks like it's bigger than 0. Where do we move? Left. So we're going to go C units left. So we're going to change this to C units, and then we're going left. And when C looks like it's negative, just right like this and like this, we're going to move C units to the right. So just one more summary. Any numbers that are added outside, it's going to move the functions up and down. And it's very logical, this one. Positive means up, negative moves down. This makes sense. Any adding or subtracting inside the function where the x is, it's going to move it left and right. And this one's opposite than what we think is going to happen. When it's positive, it actually goes left, and when it's negative, it goes right. So when we're adding and subtracting on the outside, everything's normal. On the inside, everything's opposite what we might think it is. So let's take a look at these examples and just list the parent function, and then just list what transformations we have to apply to do these. So here we have x squared plus 5. What's the parent function? What's the original? Well, it must be y equals x squared. So we must start with x squared, and then we have to ask ourselves, what is that 5? What position is it in? Is it outside like D, or is it inside like C? Well, it's outside the squared, so this is D. This is D. It looks like this guy here. So I'm going to put a little D on top. So that means this 5 is going to affect the vertical shift. So it's either going to go up or down. And following this little rule here, when D is greater than 0, we're going to go up. So we're going to move all the points up 5 units. How about the next one here? First of all, what's our original graph? Well, I can see it's sine. So our parent function is we're going to start with the graph of sine x. And then this -1 here, which position is it? Does it look like D, or does it look like C? Well, it's inside where the x is, so it has to be C. So this guy is C. So according to C, when it looks like it's negative, so when it looks like it's -1, we're going to the right. So this actually means we're going right 1. Let's try another one. Can you figure this one out by yourself? If you think you can, pause the video. If you think you still need help, then stay with me. Now we have 2 numbers here. First, let's figure out what is the original graph. Well, I see a squared here. So this was originally x squared. So our original graph is y equals x squared. So we sketch that out first. And then what position is 3 in? 3 is in beside where the x is. So this must be C. So I'm going to write that this one's C. And how about this one, this -1 on the outside? That must be D. It's outside the function, so this guy has to be D. So let's apply them one by one. What is this C doing? It looks positive, so it looks like it's greater than 0, so we're going left. And so we have to shift this graph left 3 units. And then, oh, I should have done that one in blue. To be too confusing. Okay, left 3 units, that's what C is going to do. And then let's do D. D is outside and it's positive. And if we look at our little cheat sheet over here, it's negative. D is negative. When we look at our cheat sheet, that means we're going down 1 unit. Down 1 unit. Let's try actually sketching these now. So we're going to do one together, and then you're going to try the next one on your own. So we're going to start off by making just a list of what we have to do, just like we did in the previous question. So first, let's list out the parent graph here. So the parent graph must be, I see an x here and I see a squared. So the original must be starting with y equals x squared. So there's our original graph. We're only going to be dealing with 2 different paragraphs, so it's either this one or sine. And then we got to figure out what transformations are here. Well, if you go back to our previous page, C is any number that's add or subtracted directly to the x inside the function, and then we have D, this must be D, it's outside the function. So if we go back to our cheat sheet, what does this mean as a transformation? If C looks negative, everything happening inside the function, it's opposite of how we think it's going to be. So it looks negative. What's actually going to happen? We're going to go to the, looks like it's going to be left, but it's right 4. And just go back to that cheat sheet on the other page if you're still confused by that. And then D is outside the function, so we know it's going to affect, it's going up and down. And D is just logical. If it says take away 3, guess where this is going? We're going down 3. So here's what we're going to do. It's really as easy as this. This is the hardest part, coming up with the list, decoding what's happening. We're going to draw out our original graph. We're going to shift it right 4 and down 3. And so in the first part of this lesson, I said we have to be able to graph these super fast. And when I say super fast, I mean super fast. It should be this quick I realize, okay, I've got 1 point here, 1 point here, 1 point here, and then 1, 2, 3, 4 here. That's how fast it should be. So you have to practice sketching these over and over and over again, just so that you get really used to graphing out our original parent graphs, okay? So that's how quick it should be. If you're not there yet, if you need to flip back to the first page, keep doing that until you know really, really well that y equals x squared, the points are 0, 0, 1, 1, 2, 4, and then the opposite. So now in one step, we're going to move every single point right 4 and down 3. So here we go. I'm going to start with this point. We're going to go right 4. So 1, 2, 3, 4, and then down 3. 1, 2, 3, and then we're going to put a dot. And then we're going to do the same thing to every other point. So I'm going to move this point. 1, 2, 3, 4, and then down 1, 2, 3, and put a dot. So now do the same for the rest of the points. Okay, so we should have 5 points over here. So pause the video, move every point right 4, down 3, and then come back to the video once you're done. So your point should look something like this. Let's connect them all. So we know this is going to make a parabola. So we're going to connect this all with a smooth curve in the shape of a parabola. And we're done. We're going to label our final graph. So this is the graph of y equals x minus 4 all squared minus 3. Now let's try this one. You should be able to do this one on your own now. So pause the video and try to sketch this on your own. I'm not going to go through it step by step. So when you come back, we're just going to check your answers. So pause the video now. If you've restarted the video, you should just be checking your answers now. Okay, so first check. Did you realize that this was our parent graph and that we're going left 5 and up 1? Because here is our C value. So it looks like it's going to the right 5, but it's actually going left 5. And then here's our D value. It's moving it up 1. Next, did you sketch out the original parent graph? Note, if you can get the final answer without drawing the parent graph, that's fine. Drawing the parent graph is not a necessary step. It's just very helpful. Next step, did you move every single point left 5 and up 1? And did you connect it as one smooth parabola? Last step, label. So this is the graph of y equals x plus 5 all squared plus 1. Let's apply the same idea now just to the sine graph. So this should be repetitive now. Hopefully you look at this and think, I can do this. So let's just start this off together and then you can go ahead and try it on your own. So here we know we've got a different parent graph now. So now we're going to start off with the graph of y equals sine x. And then we have to decide what these numbers are doing. So we know that this guy here is in the C position. So this is our C. And this one is in our D position. So what does this mean? C, we know we're going left and right, so we know we're going to move left 30. In this case, it's degrees. So we're going to move left 30 degrees. By left, I am absolutely wrong. Hopefully you're looking at that saying, no, that's not right. We're moving right. When it's negative, it looks like it's going to go to the left, but it's actually moving right. So we're moving right 30. And then this D is positive, so we're going to move up 1. So there's our to-do list. First, let's draw a sine so we know what sine looks like. Okay, we know that we need to get on the x-axis, we know we're going to go from 0 to 360. We're going to move to the right 30. So it makes sense to make sure that if we're moving everything to the right 30, that we have 30 degrees is very easy to figure out how many spaces it would be. So I'm actually just going to go up by 30s here. So I'm going to go, every 2 squares is 30. So 30, 60, and then I'm going to put a 90 here. And then we're going to do another 30, 60, and then 180. And then I've got, add another 90, and we've got 270, and add another 90, and we have 360. So we need to have a good understanding of the original sine graph. Okay, for our y values now, we know normally sine goes up to 1 and down to -1. Keep in mind we're going to be moving up 1. The whole thing is going to get moved up 1 unit, so it doesn't make sense to make this one and this one. Why don't I just make 2 squares 1 unit? Then it's really easy for me to move everything up 1. This is not the only scale that you can use, but this is a scale that makes a lot of sense. So from the first page, we're going to quickly sketch out sine. So you need to know these points really, really well. I'll tell you my trick. I know that sine generally looks like this. Okay, it goes up, down, back again. So I start with the first point on the x-axis. Here we go. And I know that in the end, it's going to end in the same place. It's going to end at 360. So I had my point there. And then I start working in the middle. So I know it's going to come up, hit, down. It's going to hit exactly in the middle of 0 and 360, so that's going to be 180. Then I know in between 0 and 180, sine is perfectly symmetrical. So in the middle, it's going to hit its maximum of 1. So in the middle is 90, and here it hits its maximum of 1. And then we know in between 180, that's when it's going to come down. In between 180 and 360, it's going to hit at 270, and it's going to hit its minimum at -1. And now we can just connect it all. So we just got to get really fast about sketching this one. And now all I have to do is my to-do list here. Move everything right 30 and up 1. So here we go. I'm going to start with this point here. What did I decide 30 degrees are? I decided that 2 squares was 30 degrees. 30, 60, 90. So I got to move everything 2 squares to the right. And then up 1. Does that mean 1 square? It means 1 unit. And so I decided that 2 squares was 1 unit going this way. So I have to move it actually 2 squares to the right and 2 squares up. And then I'm going to put a dot. And now I'm going to do it for the next number. 2 squares over and 2 squares up, and we're going to put another dot. Continue this pattern for the other points now, and then come back to the video. So here's what your final graph should look like. Connect it. And we're done. For this last guy here, try to sketch this on your own. So first come up with your list, and then draw your original graph and move your points. And then just come back to the video to check your answer. So go do that now. If you're back at the video, you're just checking your answers now. So here is your to-do list that you should have come up with. We're going to draw out the original graph, y equals sine x. We're going to move it to the right 90 and down 2. Next, did you draw a scale? Noting that we need to move it right 90. So it's going to, sine is usually going to end at 360 if we're just drawing one cycle of it. But we're going to need to move it over 90. So we really need to get to 360 plus 90, which is 420. So did you leave enough room for that? And also for your scale on your y-axis, normally sine just goes up to 1, but it's going to get shifted down 2. So the minimum is going to be -1 typically, but we're going to have to go shift down 2 to -3. So did you make sure that you got to -3 on your scale? Next, did you sketch out the original sine x? I'm going to do this one in front of you just to remember. I do the first one in the last point last, and then the middle, and then I know at 90 it has to reach its maximum, and at 270 it has to reach its minimum. Once you have sine sketched, did you move every single point to the right 90 and down 2? Remembering that 90 defined on my scale is actually 1, 2, 3, 4, 5, 6 squares. So I have to move every point 6 squares to the right, and down 2, for me, that's going to be 4 squares down 2. 1, 2, 3, 4. So every one of my points needs to be moved to the right 6 squares and down 2. So here is what it should look like. We're going to connect it. So our final points is to check should be at 420 and -2. And our first point should be at 90 and -2. And we're done.